Swayam Prabha. Digital India. Educated India.
This is lecture number 2. Welcome everyone, and today we are going to take it forward where we started. So, in the last class we discussed about different applications of CFD. We saw that CFD is used in almost every dimension of our life, okay, whether it is designing equipment, whether it is related to the healthcare, or whether it is related to some luxury, some sports like designing an F1 car, or let us say you want to design even some sports equipment. So, there also CFD is used, right. So, we saw applications in mechanical, chemical engineering, automotive engineering. I mean, of course, there are many applications which we did not cover in the last class, but what we wanted to give you a flavor is that the CFD is used in every sphere of our life. Okay. So, today we start with the question that why we need CFD, right. Of course, we discussed some aspects of it in the last class, okay, but it is very important that when we already have very sophisticated tools with which we can perform experiment. So, do we even need CFD, okay, or why it is becoming so popular, why everyone is using CFD, right. And what are the basically qualities of CFD which is basically which you cannot get from the experiment, right. So, let us compare parameter by parameter between the CFD and experiment, okay. The first and the most important parameter is the cost, right. So, naturally if you want to build a thing, let us say you want to start a lab and you want to see the flow happening on a cylinder, right. So, you have to basically there are cost involved with the building the lab, then purchasing the equipment, you might want a laser, you might want a tunnel, okay, you might have want to get a high speed camera and all those things, and then every time you perform the experiment, right, it is going to cost you I mean certain money, right. Compare that to an experiment tool, right. So, let us say you have a validated code, okay, which took some effort, okay. I am not saying that it did not take effort, it may have taken some years, or you might have purchased a commercial developer, right. So, you have put some initial cost, okay, but after that let us say you want to run the same problem, understand what is happening on a flow past a cylinder, okay, you could simulate it easily without basically incurring a lot of cost compared to what you had in the experiment, right. So, that way it is generally more economic than an experiment, okay. The second thing is time, okay. The time that you require to simulate a flow using a model typically is much shorter than the time to basically set up the experiment, run it, capture the data and basically ensure that the experiment has run properly, right. So, it basically saves your cost, it saves your time, okay. The third very important factor is the scale, right. So, let us say you are designing an aircraft, okay, and the aircraft is of a size of a A320, and if you want to basically test it in an experiment in an experimental lab or in a wind tunnel, right. So, you need to design quite a big wind tunnel if you want to basically extract all the flow features related to very small component to the very big component, right. So, you have to basically design a very big wind tunnel where you can capture the flow phenomena in the aircraft, okay. On the other hand, it does not matter in CFD what is your scale, okay, as we will see in the next classes is that all that matters. So, you have a certain design, you will put a domain around it, okay, and as long as you are able to satisfy some of the dynamical parameters which governs the flow, for example, the Reynolds number and the Mach number, and depending on certain situations you will have different numbers which are basically the dynamical numbers which governs the flow, right. So, as long as you can satisfy, the scale does not matter. Okay. In fact, most of the simulations which are performed in this industry are the non-dimensional simulation, right. So, basically your chord length may be 1 meter or it may be 1 centimeter or it may be hundreds of meters, right. It does not matter, because ultimately you would be using that chord length to define quantity like your Reynolds number, and if you can satisfy that Reynolds number, you can simulate that, and you can appropriately multiply the values that you are getting, the non-dimensional values, for example, your coefficient of pressure or the coefficient of lift or coefficient of drag with the dimensional parameter to get the dimensional values, right. So, that is another advantage of CFD. The fourth advantage is the information which is very crucial. Okay. In the experimental data, you cannot resolve as much as you can resolve in your CFD. Okay. CFD you can put enormous number of grid points around a body. So, if you are doing a flow past a cylinder, let us take that example, because we have been discussing that, right. So, you can make a grid around that, okay, and then you can put as many points as you want, okay, on this cylinder. Okay. So, I mean, those who have not done performed any CFD calculation as of now, do not worry, we will discuss about how to make grids and why the grid is important, but this is let us say kind of O grid that I am making for the circular cylinder, right. So, you can resolve the grid as much as you want, okay, around the body, and what is the benefit of resolving the grid? That you can calculate the quantities which depends on the gradient much better. What are the quantities that depends on the gradient? For example, if you want to calculate the vorticity, right. So, for example, in the 2D case it will be del u by del y minus del v by del x, right. So, something like that, right. So, any swirl in the flow field, rotation in the flow field, let us say you want to calculate the wall gradient, right. Let us say you are interested at that what is the skin friction drag on the body, right. So, then the skin friction drag is given by Cf, okay, you can calculate the skin friction first and then you can calculate the drag. So, Cf is basically tau w by half rho u square, right. So, what is tau w here is mu del u by del y at y equal to 0, which is at wall by half rho u square, right. So, this portion that you see on the top mu del u by del y at y equal to 0, you can get this gradient del u by del y. Similarly, you can have heat transfer. So, you can have Nusselt number which depends on the del T by del y, which is basically the temperature gradient, right. So, all these gradients are better calculated in your CFD calculation than the experiment, because experiments you have limitations that how close you can go to the wall. Okay, you might have to put some probes or you want to might have to put some tracer particles, but then you also have to ensure that they are not interfering with the fluid flow. Okay, so, that is very important, because if they are interfering, then you are not getting the correct dynamics, right. You do not have that problem in CFD. So, so that is another good aspect, that you can get a great amount of information from a CFD simulation. In fact, in many of the standard research labs, you would see that you would have a lab that will be used for performing experiments, and then you would have a very good tool to do the CFD simulation of the same, and then you match first the CFD with the experiment, because that is very important, that you are able to match the gross parameters at least with the experimental data. But once you have validated your code and the results are matching with the experimental data, now you can look at your CFD data set in a great detail, okay, and now you can analyze the quantities of interest which depends on the gradient. Okay, for example, your skin friction or vorticity or all those kind of things. Okay. So, there you would your CFD data set will give you a much better picture. Okay. So, that is the fourth point. The fifth point is repeatability. Okay. So, the experiment when you perform an experimentalist, I am sure you might be knowing that it depends when you are conducting the experiment. What is the temperature of the environment, what is the humidity, okay, what is the pressure, all these things will matter on the outcome of the experiment, right. So, whether you are performing during the day, whether performing during the night, okay. So, you may get slightly different results or sometimes very different results. Those problems are not there in CFD, okay, because you have established your numerical method, you have a code and you have an algorithms, okay, and if you are not changing any parameter, you are going to get the same result from your simulation, okay. Safety is another big concern, right. So, when you are performing experiment, you have to be very careful about the safety issues, because sometimes it may be very hazardous, okay. You do not have those issues in CFD, because it is always safe, because it is happening on your computer, okay. Next is parametric study. So, that is also quite easy in CFD, and it is more difficult in experiment, just because of the fact that experiments take time and experiments basically are more expensive, right. So, if you want to, let us say you have validated your data set with an experimental data, and now you want to change certain parameter. Let us say you want to increase the Reynolds number, you want to increase the Mach number, or some other thing you want to change, you want to change the angle of attack. You could just tweak that in your basically boundary condition or whatever your input parameter, and you can quickly run the simulation, right. For experiments, it is not that easy to perform that experimental study. For example, let us say if you are doing flow over an aerofoil, okay, and you want to get the CL versus alpha curve, okay, which is something like this, okay. This is your CL versus alpha, okay. Now, this is CL naught, okay. So, if you want to do that, let us say you have an aerofoil, okay, you keep on changing this angle of attack and you can get new results, okay. If you want to do the same thing in experiment, you have to basically always change your aerofoil or the wing that you are doing, okay, and run the experiment once again, calculate the data set, process it, and it's not that easy to perform so many studies with experiments, okay. So, that is the parametric studies are not very common with in experiments, okay. The next is the effect isolation, okay, and this is a very important thing, okay. Let us say you let us talk about a supersonic flow, okay, and those who have done flows or compressible gas dynamics, you might have heard about the shock and bond layer interaction, okay. The shocks form, they interact with the boundary layer, okay. Now, let us say you want to find out that how much is the boundary layer is affecting the shock, right. So, what you could do in CFD, that you run an implicit calculation, okay. The shocks will form, but there will be no boundary layer, right. So, what we have done, we have isolated the effect of shock from the effect of the boundary layer, okay. It is not a physical system, you cannot have an implicit system in a practical flow, right. All flows are quite viscous and there has to be boundary layer, there has to be viscous effects, right. But for your effect isolation, you want to understand the effect of individual parameters, right. You could do an ideal system, you can do a simulation of a implicit system and find out the effect of that system, and that way you can find out whether how much is the interaction between the shock and the boundary layer, right. So, this effect isolation, which is a very specific thing to CFD, where you can simulate an ideal system, you can take out some effect, you can add some effect that can be artificial, but that can give you certain understanding of the flow phenomenon that is happening, okay. This we already discussed that experiments are intrusive, okay. Let us say you want to measure the wall flux, okay. You would if you want to, I mean nowadays of course you have pressure sensitive pens or temperature sensitive pens that can give you some of those information, okay. But let us say if you are putting a probe or something, okay, so then it will interfere with the flow itself. Secondly, if the boundary layer is very thin, It is very difficult to put design a probe which is of that order of the size of the boundary layer and very close to the wall, and which is not interfering with the flow itself, right. So, the experiments can be intrusive, okay, because you want to understand the effect, and when the instrument that you are using to understand the effect is changing the dynamics itself, right. So, then you are effectively not understanding certain aspect that you are trying to figure out. Okay. So, in that cases CFD is very helpful. Okay. And safety we have discussed, okay, that CFD is always safe, it is a repeat here, and experiments it may be hazardous. The feasibility is also very important thing in CFD. So, let us say you want to send a rocket to the space, okay, and you are designing a space shuttle, okay. You cannot basically run, I mean, 10 experiments to see whether the rocket is able to, I mean, you are able to propel it in the sky or not, right. But you can do 10 simulations on your computer and see how the performance of the individual component is, whether you are getting the desired results or not. There are certain basically systems which where the temperature rises very high. So, even if you are able to do the experiment, you cannot measure it, right, because you cannot design a probe which can sustain that kind of temperature, right. So, these are all those difficulties are there in the experiments. So, where it is just not feasible to do the experiment or collect an experimental data, but you can perform CFD simulation of those kind of systems. And lastly, very important thing where experiments basically are basically beat CFD is the reliability. Okay. So, normally typically if you are a good experimentalist, the data that you are getting is treated as a truth model, okay, in the sense that what is you are saying, what is happening, or you can analyze that and you can describe that. Okay. CFD more or less always need to be validated with some experimental data before you use it for a new case or new study, right. So, that is very important thing, that the experiments are reliable, okay. You have more trust on the experimental results that you are seeing than basically the CFD, and that is why it is always asked that you show me the comparison with the experimental data, okay. What is your grid convergence, is the results that you are getting is consistent or not. So, all these things are desired when you want to present the outcome of a CFD result. So, these are very important things. So, if you are doing CFD, you must understand that your code should be able to basically repeat some experimental data before you claim that your code is before the code can be used for a new experiment. Okay. So, these are some of the things that we discussed, difference between not the difference, but the qualities of CFD and experiment. Okay. Now, let us go to some of the basic principles of CFD. I hope I convinced you that for certain flows CFD is a very good choice and we should make use of that. Okay. So, now after that let us see that what do we mean when we say CFD. Okay. So, the first thing that we need to understand here is that computers do not understand your differential equation, right. So, the governing equations that we have has got certain differential equations. You can have the temporal term, basically a time dependent term, or you can have the spatial term where the gradients depend on the space or the spatial gradients, right. So, but your computer does not understand those symbolic math, okay, the calculus, right. So, what computer understands, it can do arithmetic very well, okay. If you ask it to do an addition or a subtraction or even multiplication, division, so those things computer can do very well. So, what we need to do, that we need to somehow change our the differential equation or a continuous function into a discrete function, so that we can find out whatever gradients that we want to calculate, right. So, here for example, you have the continuous curve, okay, and if you want to find out, let us say I am interested that what is the gradient at this point, right. So, if you have a curve going through this, right, let us say you can define this is my f x and this is my x, right. So, if you know that how f x is, you can get this f prime x and you can get it at this given x value, right, if you know the nature of the curve, right. To get this same f prime x here, okay, what we need to do is that you need to discretize this domain. Okay. It may be a continuous curve, but you would now put certain approximation, you will put some points on this curve, okay, separated by some distance, okay, and then assign these values in your computer memory, okay, and then what you could do is that you can use any of the algorithms. So, that you have might have studied in your math course to get the gradient, right. So, here for example, if I want to get this gradient here, okay, let me just see. Okay. So, yeah, if you want to get this gradient here, so if you want f prime x, okay, or df x by dx. So, what you do, you will take this this is f 2 f 1, right. So, this is f 2 minus f 1 by x 2 minus x 1, right, from your very basic calculus, right. Of course, you might have read that it is correct only when limit x 2 tends to x 1, right, then only you will get this correct gradient, right. So, what you are getting now may be very inaccurate, because you are approximating a curve which is this with a straight line, right. But what you could do is that let us say what you start basically refining the grid, and you refine it so much that your grid points are very close to each other, right. So, then you can basically approximate this curve with a straight line, okay, and then you can calculate the gradient more accurately. So, that is the big crux of the CFD, when we say that the grids are very important and grids should be refined enough to calculate the gradient. Okay. So, that you can understand from this very simple system, that if you want to approximate any curve, you have to have grid points very close to each other, so that you can calculate the derivatives accurately. Okay. So, this is one of the most basic principle, that you need to have points sufficiently close that you can basically calculate the derivatives accurately. Now, that discretization can be in the space or it can be in the time. Okay. So, in the space, so if you have a grid like this, okay, or if you go to the earlier example, so this is your, what I am doing, I am discretizing it. Okay. I am subdividing my domain into certain parts, okay, and then I am naming this, let us say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay. Then you will have 11, 12 and so on and so forth. So, at every single point I am putting my variable, okay. So, I have the variable of let us say rho, u, b, p and so on and so forth, right. So, at every single point on the grid point you have these variables defined. Okay. So, this is called the spatial discretization, that in the space you have basically defined the variables, right, and these variables will talk to each other based on the underlying governing equation and your boundary condition. Okay. Now, this is the grid that you made. Now, let us say this is flow over a cavity. Okay. So, what is flow over a cavity? Okay. It is a very interesting problem, and it is a classical benchmark problem, that you have walls on 3 sides, okay, stationary wall, okay, and okay, and you have a top wall which is moving, okay, and this is called a lead. So, it is a moving lead here, okay, because this top wall is moving and all others are wall. So, what you have is basically, because of that, a vortex will develop like this. and depending on how much the speed of your top lead is, you might have additional vertices here. Okay, this will be counter rotating here and here, okay, and maybe here. Okay. And if you have if you, as you increase Reynolds number, you can have tertiary vertices also here. Okay. So, this is a very interesting problem, and you might be interested that okay, what happens, let us say you started moving the lead and what happens after t equal to let us say 5 seconds. Okay, remember this example of the lead driven cavity, this is called lead driven cavity, because we will be using this example again and again, because it is a very simple problem, right. As you can see that you can make a simple grid like this to solve the problem, right. So, let us say I want to see what happens at t equal to 5 seconds. Okay, as we will see later in time that you cannot go from 0 second to t second directly in your simulation, right. You have to obey certain laws, so that you are able to simulate it properly. So, your delta t may be let us say 5 millisecond, okay, 5 into minus 3 second, right. So, what you are doing, you are discretizing your time into certain parts, right. So, you will have 0, delta t, 2 delta t, so on and so forth, right, until you go to like 5 seconds. So, in this case it will be the 1000 time steps, right. So, you have to discretize in time also, right. So, any equation that you will have, if you start with a let us say a linear convection equation del u by del t plus c del u by del x equal to 0. So, you have a temporal term, you have to discretize in time, you have a spatial term, you have to discretize in space, right. So, Navier-Stokes equation, which is the governing equation of fluid flow, has the temporal term as well as the spatial term, okay. And then you have to discretize the equation also. So, what is in the continuum, okay, it has to be mapped into an algebraic set of equations, and once you have these equations at every point, you solve these equations together through your time marching scheme. It can be a Runge-Kutta, it can be in Euler method, okay. There is various methods to solve it, okay. So, once you do that, you can basically solve this problem. So, this is the second principle, that you have to discretize in both space as well as time, okay. So, with that we will stop here, okay. What we will do in the next class, we will start with the steps of CFD, where we will see what are the things that we need to do when we say we are performing a CFD simulation. You will see that you have to do pre-processing, starting from the geometry cleanup to making a grid, to basically setting up a solver, run the simulation, and then you do post processing. So, we will discuss about all these things in the next class. Thank you.